Hi everyone, the topic that we are going to discuss today is creation of expression tree from prefix notation. That is, if I write it like this, prefix, from prefix notation towards, we want to do what? Create an expression tree. Okay, so I have already given you a lecture video, or you can say I have already delivered a lecture on creation of expression trees using infix notation. You can find that particular, you can say, tutorial or video from my another you can say YouTube video or other tutorial. I'll share the link in the bios as well. Okay, so now in order to create an expression tree from a prefix notation, first of all we should know what is basically a prefix notation. So prefix notation is the representation of a mathematical equation in which we encounter operators before the operand. For example, let me write an expression for you. Let's say I have got a notation like minus plus 3 power 4 multiply by 15 6 plus divide 14 3 multiplication 65 and 5. I am adding as a extra space between these characters so that we would be able to visualize this expression more clearly. Okay, this is a prefix expression. As you can see, that operator appears before, you can say, first operand. So this is the prefix representation of a standard mathematical equation. Now what we want to do is we want to create or build an expression tree from this particular given equation. Now here we should know one thing, that is basically what are the we must know what are the rules to convert prefix expression to you can say into a expression tree. So first of all, what you must do is, in order to create expression tree, start from the left side or left subtree of the given expression. Okay, so this first node will become what? Root of your tree, root of the given tree. Without giving it a second thought, just make directly this first node as a root of your given tree. Okay, so this minus will become the root. Okay, now what we do is we will start moving from left side, character by character, towards the right side until we found the end of this expression and build the expression tree accordingly. Now how we will you can say do this type of operation, or how we will basically create an expression tree from this particular prefix representation. Okay, so as I have told you earlier, we will move from the left side of this particular tree and move towards the right side of you can say this particular expression, and move towards the right side till we found the end of the expression. Same goes for your expression tree as well. What we do is we will figure out one values from this side and we will insert it here, and again our insertion will be towards made towards the left side of the tree. How? Okay, I'll go step by step. So let me revise again. Number one rule is we will move towards the left side of the given expression, and the first node will become the root of this expression tree. Okay, we have inserted this minus. Now next is this plus. We are going to insert this plus. Okay, in this particular tree, or in this particular you can say expression tree where we have only inserted the root node so far, what we do is we will insert this particular plus towards the right side of the parent. Oh sorry, left side of the parent. Why? Because you can say that this is the rule number 2. That is, whenever we have whatever the character we encountered here in a sequence, that is after minus we encountered plus, we will directly insert it towards the left side of the parent node. Okay, I usually make it easier, like you can say whenever I try to memorize it, I make it like this, that since this is a prefix expression, every operator appears at the left side and we are traversing this particular notation from the left side as well. So we will insert every node at the left side of the tree as a priority. Okay, so here I have inserted plus as a, you can say, left side or left node of this particular parent or this minus node. Okay, so coming towards the next character that we encounter here, which is 3. So 3 will also be inserted at the, you can say, left of the parent node and left of, you can say, very immediate parent node. Okay, we will keep on doing this left insertions till when, until unless we found an operand. Okay, let me revise it again. Here I found a operator. I directly made it a root node. Since the definition of expression tree state that all the operators will become the part of intermediate node, but no operand will appear at intermediate node, or in other words, all the operands will appear at the leaf node. They won't be having any child, not even a single child. Okay, so it cannot have likely branches like this or trees like this. Okay, so when we encounter an operand here like this, I have encountered an operand 3 here, so I'll just make it you can say stop here. I won't go for any further insertion at this side, and then again I repeat these steps again and again. What is the next you can say enqueued character, which is power? I have to insert this power in this tree. So what I do is, since the left subtree of this class is complete, now we will go towards the you can say creating or building the right subtree of this particular operator. Here we don't look at the root node or the parent of parent node. We will directly try to complete a particular level or a particular parent for whose we have, you can say, found the operand. Here like this we have found 3 here, so we will try to complete its right subpart. Here we have inserted power, then again I'll go towards this expression and figure out what is the next character, which is 4, and make it as a left child of this particular parent node. Okay, since this is also an you can say operand, I won't go for any further branching. I'll go for, you can say, next character, which is multiplication here, and directly insert this particular multiplication at this node as a, you can say, right node or right child of this particular power node. Okay ji. So here you can say this level is also complete, but this is, you can say, an operator which needs basically the, you can say, operand in order to perform the operation. So I'll go towards this expression again, read next character, which is 15. So 15 will become the left child of this node, and next character is 6. 6 will become the right child of this particular multiplication node. Okay ji, here you have witnessed that whenever I encounter any operand, I just make full stop here and don't insert any more child and directly go towards the immediate parent. Here you can see that all these you can say parent nodes are now, you can say, complete. The left subtree of this minus node or this root is complete. Now next step is to fill the right side. You see, we are repeating the same steps again and again and again and again. So in here side, this side, I also go for, you can say, creating or establishing trees, just like I have made here. I have built, you can say, this portion of, or you can say this subtree of the minus node. Okay, so the next character that we encountered in this expression is plus. So I'll insert plus over here. I can't go at this side because this side is already complete. I have you can say here found all the operands that are sufficient in order to perform these 3 operations. So now all my focus will be on the creating or building the right subtree of this particular minus node. So after inserting this plus node, I'll go towards the next character, which is division. So here division will become the part of this side, and next one is 14. 14 will become, you can say, the part of again this left subtree like this. We will go on inserting at the left subtree until unless we found or we have achieved the leaf node. Okay, what is the next, you can say, a character, which is 3. So 3 will become the right child of this particular node. Okay, next character is multiplication. I'll insert multiplication over here like this as the right child of parent because left subtree is already filled. So here, what is the next, you can say, character, which is 65. 65 will be inserted here, and the next one is 5. So 5 will be inserted over here. So now you can see this is a valid binary tree, and we can say this for sure because all the leaf nodes are containing operands and all the intermediate nodes are having operators as, you can say, their as their values or as their final thing. Okay, now in order to convert or figure out any infix notation or postfix notation, we will just directly do some traversal. That is, in order to figure out its particular or its you can say infix value, I'll do in-order traversal. In-order traversal. The reference of, you can say, these traversal can be found in my other or detail of this traversal algorithm can be found in my other lecture tutorial. You can watch them as a reference. Just to give you a short you can say overview, in order traversal, what we do is we first of all call the left subtree, then print the value of node, and then call the right subtree. And this left subtree and right subtree will call themselves recursively, and in the center they'll go for the printing of a particular node. That is, when I am standing at this particular node, minus will give call to the left of its child, and this will give call to the immediate left value of this child. So if I try to do the you can say in-order traversal of this particular expression, so what I will get here is left will give call to its left, and it will give call to its left until unless I have got no value in the left subtree. And then second operation will be to print itself. So the first thing that will be printed would be 3. Then it will call its parent. Since left subtree of the plus operator has returned, so this operator will be printed. Similarly, it will you can say go and call its right subtree, and again this procedure will go on repeating itself again and again. So the expression would become something like this, that I have added 3, then print itself, then go to right, go to left, print itself, then you can say go to right, since right is null, so this will return print itself, then go towards the you can say right side, and then again left side, so it will become 15 multiplied by 6, and this whole left part will return, and this minus will be printed out, and then it call its right subtree here. Right subtree recursively call itself, so it will call its left side, left will call its left side, and the thing that will be printed is 14, and then divided by 3, print itself plus when we encounter this node, it will go and call its left subtree, so the thing that will be printed is 65 multiplied by 5. Okay, so now here I have given you you can say I have converted this expression tree or obtained the infix notation of this given particular prefix notation. This is how you create an expression tree from a given prefix tree, and you can figure out any traversal on that. There is another type of traversal that is known as post order traversal. And for this traversal, what we do is we will traverse left node first, then right subtree first, and then in the end we will print the calling function or calling node. Similarly, just like I have computed this particular equation, you can figure out the value of this particular or result of this particular traversal in order to find postfix notation or postfix expression of this particular you can say this in prefix expression. This is how basically you can convert it in any form. If you take this expression and try to build expression tree out of it, you will get exactly same expression tree, and if from that you want to find prefix expression, you would be having this expression in the end. Okay, so to give you an idea about the post order version or postfix notation from this particular expression tree, let us apply this algorithm on this given graph. Okay, so first of all, what we will do is we will go towards the left and then go towards the left until unless we encountered null. So here we encountered null, we go towards the right, we encountered null, so we will print node itself 3, then it will move towards 5. Since the left subtree of 5 has returned here, we will move towards the right part or right portion of this particular subtree that we are or this particular node that we are discussing. So the right is power here. Since its left child is not null, the function recursively call itself, so it will move towards the left subtree. When it moves towards the left subtree, it will call its left and right and then print itself. So 3, 4, and same thing will repeat over here. We will get 15, then 6, then multiplication, then power, and then addition, and this will cover all my part of the tree, this portion of a particular tree. Okay, now since left subtree of this tree has returned, I'll move towards the right subtree, and when it comes towards the right subtree, you can see that the right subtree is plus, whose left subtree is not null, and again the left subtree of this division is also not null, but the left subtree of 14 is null, so it will call the right subtree of 14, which is also null, so it will print itself, that is it will print 14. Similarly, after printing 14, it will return back to the division. Since the left subtree of this division has returned here, it will call the right subtree, which is 3. Okay, at 3, when right subtree this function call itself again, it will look for the left subtree, which is null, then it will look for the right subtree of 3, which is also null, then it will print itself, that is it will print 3. Now since right subtree has also returned, so here the division operator will print itself and return to the calling function, which is or calling operator, which is here plus. Okay, so when we move towards this plus, its left subtree has returned. Now it will give call to the right subtree. Okay, when it gives call to this right subtree, it will again call itself, function will again call itself recursively, and it will give call to the left of multiplication. When we come here, it will give again recursively call to itself, and since its left is null, right of 65 is null, it will print 65 directly here. And then again it will return to the parent node. Left tree has returned. Now it will give call to the right tree. Here in case of 5 also, left and right subtrees are null, so it will print 5 like this, and in the end multiplication will print because both of these trees have returned. This function will return to this, since left and right both trees have returned, so plus will print itself. Okay, and then this plus will return, and in the end minus will be printed. So you can basically cross check by creating expression tree from any of these expression, and you will land at the same expression tree. And you can even use stack in order to do the conversion between infix to postfix or prefix or these notations at any particular time. So this is basically, you can say, one of the example in which we have basically used prefix notation and converted it into the expression trees, and from that particular expression tree we have figured out the infix notation and postfix notation as well. Okay ji, let's discuss another example here to give you more clear idea about the prefix to expression tree creation or prefix to expression tree formalization. Okay, so let's say here I'll create another tree with different values. Let's say I have multiplication plus division a, b, c minus plus d power e, f, let's say division, let's say g and h. This is also a tree having large number of nodes, so we will quickly try to build an expression tree out of it, or build a basic you can say expression tree out of this particular prefix notation. Okay, so again this node start from the left side, so this node will become my parent node. So the first value or the first node will, or root node will become this multiplication. Okay, after inserting this multiplication, you can see I am moving towards the next node, which is this plus. This will become the left child of the parent node. Okay, then again I have got multiplication, division will become again the left child of the parent node. Okay, now we have encountered an operand which will become left of the multiplication node, but this basically stop this left insertion, and now after receiving this particular operand we will move towards the right subtree of this immediate parent. So we have received b, so luckily this left, you can say left, after returning from this left side of this multiplication node, the only node that we need to insert here is b, and this is operand, so we don't need to insert any further nodes here. Now Now we will move towards this parent, which is parent of this multiplication node, and insert the next character to the right of it, which luckily here is C. So again there is no further child of this particular node because this C is an operand. Okay ji. So what is next operator? Minus. So I'll directly insert at the right of the root node, minus node, because since left subtree is complete, operand cannot have even a single child, so we won't be going for any further insertions at this location. So we inserted minus over here. Next is plus. So plus will become, you can say, left child, and we encounter D. Okay, D will become the again the left child of plus, but since this is an operand, we won't go for further insertion. Next character is power. We will insert power as a sibling of D. Next one is E. So E will become the left child of this power node, and next character that we encountered here is F. So F will become the left child or right child of this particular power node. Now you see this part is also, you can say, a complete part, complete tree. So all the tree beyond this pen or this subtree is basically complete expression tree. Now we go towards fulfilling or finalizing this remaining portion, because binary minus is a binary operator. We cannot leave it like this as a dangling pointer. Okay, so the next thing that we encounter is division characters. So division would directly be inserted over here. Next thing is G, and next character is H. Okay, so this is how we basically have created an expression tree out of the given infix expression, and you can basically figure out infix notation, postfix notation just by performing Inorder or post-order traversal from this particular tree. If you are not so sure that whether you have created the same or the, you can say, correct expression tree for this given infix notation, you can apply prefix traversal on this given tree and you will obtain the same result. That is, if I go to you can say, apply prefix, or you can say if I want to find prefix notation of this particular expression tree, what I have to do is, in order to calculate this, I have to go for pre-order traversal. And as a result of this applying pre-order traversal over here, where I will land is I will receive the exact same expression from where I started the whole calculation or the original expression. So this is how you can basically cross-check that how you would be able to create expression tree from the given prefix notation, and how you can cross check back or how basically you can create a tree from or you can say prefix notation from an given or the created expression tree. Okay, in order to find infix notation over here, what we will do, we will apply Inorder traversal, and in order to get the postfix notation of this given expression is, we will apply post-order traversal on the given tree. Okay ji, this basically concludes this lecture. So if you have any question or any query, please do comment on this given video on the comment section of this video. I'll try to get back to you as soon as possible. If you have any query, I'll try to resolve it. Okay ji, if you like this video, please press the like button and do subscribe my channel. Thank you for watching.